In this video, I am going to discuss about sulfur dioxide molecule, hybridization, Lewis structure, and some of the details of its bonding. Let us draw the basic skeleton. Then we have to count the number of valence shell electrons that are going to be available for this bond formation. Both sulfur and oxygen atoms give 6 electrons by each to their valence shell. Then we can multiply 6 into 3 means 80. Then I am going to complete the octet of these two oxygen atoms. I used 16 electrons here, then 2 remaining. Those 2 should go to the sulfur atom. Now still, the octet of the center sulfur atom has not completed. Then I have to take 2 electrons, resulting in a double bond. Like this. Now I am going to determine the formal charges. I will number the oxygen atom 1 and 2. 1, 2 and sulfur atom. Each has 6 electrons in the valence. This one 4 lone pair electrons and 2 from the bonding pairs. It adds up to 6. Second one 6 lone pair electrons and 1 from the bonding pairs. It adds up to 7. When you come to this sulfur atom, 2 from lone pair, 2 from the bonding pair, 1 from the bonding pair. It means 5. 0, minus 1, plus 1. Second oxygen atom should bear the negative charge and center sulfur atom should bear plus charge. Now here you might wonder why the sulfur atom doesn't go up to 12 electrons. To answer that, we have to consider the hybridization of sulfur atom. Now this is the valence shell electron configuration of sulfur atom. Sulfur has plus charge in the Lewis structure, so I have removed 1 electron from the valence shell, so it should be P3, not P4. Now sulfur atom requires 3 hybridized orbital because it has 1 lone pair and 2 bonding pairs. To fulfill that, sulfur atom should make 3 VSEPR units. So we can take 1 from S and 2 from P. So there's a remaining 1 single electron with orbital, so that can be used to make the 5 bond. Now this should be sp2 hybridization. Now let us look at the other possible Lewis structure for sulfur dioxide. In this structure, sulfur has 2 double bonds. Still, it requires 3 VSEPR units and 3 hybridized orbitals. The difference here is sulfur requires to form 1 extra 5 bond because it has 2 5 bonds. When we come to the electron configuration for the hybridization, we have to have 3 hybridized orbitals, but we have only 2 orbitals with unpaired electrons. Since we have to make 2 sigma bonds, we have to have 2 orbitals with unpaired electron. That is okay, but the problem is we have to make 5 bonds. To make 5 bonds, we have to transfer 1 electron to d orbital. This process requires some energy. But if you can remember the earlier one, it doesn't require this kind of transfer. Thus, a competition will create. Because of this reason, the sulfur dioxide favor 1 double bond and 1 single bond. That is the earlier Lewis structure. Anyway, if we further continue this one, I will take 1 from S, 2 from P with the lone pair, and 2 single electrons with 2 orbitals. 1 from P and 1 from D should be used to make the 5 bond. And these are going to sp2 hybridized orbitals. Anyway, earlier Lewis structure, that is the more preferable one because of this energy requirement. Now let us go to the early Lewis structure and determine the oxidation numbers. There are 2 oxygen atoms and sulfate. When we consider this oxygen, it looks like neutral, but it has double bond, and oxygen is more electronegative than sulfur atom, so it can withdraw 2 electrons from this double bond in addition to the electrons given by oxygen atom. Therefore, oxygen 1, the oxidation number should be -2. When we come to sulfur atom, it has 1 double bond and 1 single bond. From the double bond, sulfur loses 2 electrons. From the single bond, sulfur loses 1 electron. The reason is oxygen is more electronegative than sulfur, and oxygen withdraw 1 electron from each single bond. With the positive charge available, all should be added to plus. When we come to oxygen number 2, it already has a negative charge. With the single bond, it can get negative charge, altogether -2. Now let us go to the geometry. 3 VACPR units, 2 bonding pairs and 1 lone pair. The lone pair create the repulsion between the bonding pair electrons. This will make 2 sulfur-oxygen bonds push down further and occupy the bent structure. If we consider the electron pair geometry, it should be trigonal planar, but bonding pair geometry, it should be bent. Now, if I draw the trigonal planar structure, this should be 120 degrees. But because of this repulsion from the lone pair, this bond should be less than 1 to it. That is how we guess the approximate bonding angle for this one. So this would be less than 120 degrees. But since only 1 lone pair, this should not be too much less than 120 degrees. Now this is the geometry of sulfur dioxide molecule. You can see the bent structure. So I remove the electron cloud, and all the 3 atoms can occupy one single plane like this. You can see they are aligned in one plane, and here it show only the bonding pairs, but if we consider the lone pair, it occupies the trigonal planar geometry. So this is the electron cloud. You can see this is how normally sulfur dioxide molecule behave.